All right, let's talk about some branching networks. Okay. So there will be some problems here, right? I'll give you some assignment questions for this. It's a good thing to figure out. So, branching networks, right? So if you've ever looked, you've been in a plane or just seen pictures of the landscape, there's this beautiful kind of fractal structure, right? Mountain ranges and all these sorts of things. But river networks are these. Here's a little doodly example. This branching structure. We have them inside us too, right? So our blood networks, we have the arterial structure and then the venal network, right? So it's this coupling of two branching networks. Out from the heart, branches, goes through the capillaries or capillaries? Okay, so I say capillaries. What? Okay. There's some things that I'm losing it. You'll see some spellings that are a bit odd, like I know I put model with two L's. Okay. Yeah, I had a student who would wince every time I said capillaries. I don't know why. He would just like visibly kind of like bounce around his chair. He told me it was very painful for him to hear that. So, strange character. Okay, so that's a really interesting network, right? And so angiogenesis has to grow somehow, right? That's pretty weird. It's not a purely branching network. There's a circle of Willis, for example, right? So you've got a little, so some of you biology fans will know this one. You've got a little loop in here so that there's a supply going up on 4 different things, and you can have them occluded. So my old friend Markov, the one who handed me the complexity book years ago, said that he wants to use a brain surgeon or brain free occluded completely. So, it's a good bit of redundancy because you need to keep the scone running, right? On its 20 or 30 watts, which it somehow manages to function on. So branching networks, they're pretty important to us for us, just walking around, but they're at all scales. Okay, you can think about transportation networks in cities. Of course, we've made them. They're a little funny. Animal networks, the way people walk around. Oh, here's a good word, hodology. I was going to put this in somewhere. Germane to the animal networks thing, right? So it's the study of paths, and this idea that people, of course, you put down sidewalks or whatever, right? And then people are supposed to just walk in ways that make sense to them. And then eventually, sometimes, maybe you'll pay for that and say, fair enough, And it's interesting to see where, how rutted things can get to before someone says, okay, that really is what people walk, or they try to patch it over or something. But obviously animals do this and so on. But this is actually it's a study of pathways and sometimes for networks. Right. Interconnections of brain cells, so that's actually just networks. You've got to call it omics, connectomics, craziness. This is an interesting one. Just a fun word. Paths in a person's life space, which is pretty interesting. We often do it. We're a little bit one-dimensional, right? Because you'll have home and work and go like this, track back the same places. Two types of runners, right? The out and back runner, and then the one who always has to go in a loop. Otherwise, it's just a nightmare for them. I don't know if you noticed that.
I'm the out and back guy.
Yeah. So if you get Strava, you can take your stuff from Strava at the end of the year, and you get a little picture, right, of all the things you did. And mine are usually pretty awful, well, because they're all in the basement. But a lot of them are out and back. But you see people do these really interesting. They make very interesting splotches.
Or some people have the craziest out back, where they just go crazy zigzags and then they'll follow the zigzags back.
Well, there was a guy in Vancouver, was it, who went out of their way, really figured out in detail, like a connect the dots thing, to make really quite massive sketches, like giraffe shapes.
Oh yeah, that apparently like
Yeah, quite elaborate. walking story. Boston, no. So, I mean, of course, with city planning, right? I mean, we have some places that they're all grids, especially out in the West in the US, that have just been like, we're going to make this. Manhattan's a great example, right? It's a total disaster down the bottom, and then Houston Street is just sort of a grid. So we seem to, with the Manhattan metric, right? When we actually, that's how we measure things. There was a tweet the other day that said that the average road distance between two places in the US versus the crow flies distance is about 1.41 times as long, which is the square root of 2, right? Because when you look at the whole thing, there's a lot of grid structure. Yeah, so we made it a little odd. Hexagons, it would have been much better. Canberra is all circles, which is unbelievably confusing. When you first get there, you're always going on circles everywhere, and you just have to, yeah. It's good once you're there, but I spent a summer there and I never went on the same. Just walking, I never went the same way twice. You really were going in circles. Burley Griffin is an American architect. I don't know, maybe he was just trolling. I have an idea for you guys. But it is quite fun. Okay, walking paths. All right, Paul Hayes. Okay, so we're going to do that. And the blood network thing. Yes. Actually, so trees are kind of hard to get data on, right? Because you'd love to have all of this branching structure. That's a bit of a hard thing to get hold of with a nice big tree. For now, we have this idea of tree bumps that we've run around and kind of just like sending the signal back and do a 3D image of the tree. We have a little small tree bumps. Roots, you can pull the thing up and look at it. So that's there's some data on that. Okay. So there are a couple of different pieces here. So there's supply and collection. So one source to many sinks, things like that. So we can think of the heart, right, as one source to many sinks in 3D. Cities, kind of, with a real center to them. If you think of like downtown or midtown Manhattan, where a lot of people work, right, that's kind of sitting in this 3D world, and all these people come in and leave every day. It's got a really, and the density profile of population for Manhattan, for New York City and around is very peaked and drops away. LA is really flat. So, but there are lots of so there are many examples. Again, it's sort of physical where you have this kind of story going on, and collection other way around, right? So many sources to one sink, and that's say how river networks basically work. And you can think of the venal supply, or the venal network in us, right? We're coming back from all these capillaries or whatever they're called, back to the heart. Yeah. Okay. Yeah, lots of branching things. I mean, evolutionary trees are another interesting example, right? And, we've seen even that apply with that. So the evolutionary diagrams have been applied to stories and so forth. Organizations are hierarchically structured, but not really. Not entirely, of course. Even the military, it's not really like that. But it's a big piece of it. Okay. And river networks overall have a branching structure. Yes, there are braids, and then there's titles, the title structure. Those things are different. But there's this big aspect of branchingness. This is good. So visually, yes, straight away you see this thing has some sort of fractal scaling kind of thing, right? Lots of little tiny ones out here. And of course, we like power laws, right? So this is another power law story. We won't get to that straight away. If you randomly select a point on the network, right? So just randomly choose one in space, and look at how big the basin that's attached to it is. So you can look at the length of the main stream, so it's going to be kind of important. So you take this point and you travel up the major string, like always taking the dominant one. Look at that length, and then look at the area that's drained through that point. Then you end up with power law distributions, size distributions for those as well, right? So again, it's one of these stories where very rarely you get to here. You'll get that point. This is like picking Bill Gates out of Bezos, I should say. He's there in the front there. In there. Reasonable competition. So, that's Bezos. This is Bill Gates, right? But most of the time you get tiny ones. And in fact, most of the time, of course, you would actually not really be straight, right? You'd be out in space in between. Okay, so Mandelbrot, of course, is famous for coming up with the term fractals, but it seems that the first quantification of scaling of geometric shapes was for river networks by a guy called Horton. It's a paper in 1945. So a very famous geomorphologist or hydrologist who was thinking about these things. Mentioned trees. This is an excellent apple box. There are lots of eucalyptus trees. That's a good one. Yeah. Okay, so let's look at it a little bit. So this is 931, Waldo S. Block, which is just a great name. This is purely sort of drawn, it's hand drawn basically, and it's just the story of what happens with evolving landscapes, right? So you may have a landscape that doesn't have any drainage in it, maybe because of some rapid uplift. Right? So there's always this backdrop of geologic movement. And then so there's some initiation that it grows into the space, what's called elaboration, and then piracy. So these terms are a little strong, but piracy, which means that the divide between two valleys can move in a certain move, but this river basin, or this little basin over here, starts to collect more water. This one can backwards. So this evolution over time, where some, maybe that, lots of things happen, right? There's meandering, there is the breaking off of loops, all sorts of pieces, collapsing, slides and so on. So there can be changes in the details of the sometimes quite extreme. Okay, so this is sort of looking at this long-term history, and it's really actually just, it's a nice piece, it's quite old, but it's this, here's the lifespan of a geomorphological surface. Maybe 20 years ago, I guess now, when we were starting to get good data from Mars, this was sort of this big issue, is there water on Mars, right? And one of the things that people were looking for was, if you see some sort of branching structure, is that evidence of a river network? Or is it just, it could be just avalanching, right? So, and that was never really quite sorted out. Now we know, also about the Martians, but I kid you not, I sat on a plane the other day from here to JFK, and the guy next to me was a total conspiracy theorist. And I'm saying this because he did mention that there'd been moon bases for 1,000 years and they won't tell us about it. Also Mars. Funny thing he said about Mars was that there's only a few pictures that they show us, right? He talked about the Cabal that's been around since the Roman times. Wow, there was a lot of information. Really serious, and he said, why do they only show us a few pictures of Mars, right? Because clearly there's other stuff that there are structures and being delivered. But it turns out actually we have better imaging of Mars than the Earth, right? It's not as big, no atmosphere, we've run a bunch of little satellites around it. We have really great satellite data for Mars. Better than we have for it, because the whole cloud thing is a little messy. That's a bit bigger. Anyway, I didn't mention that. I wrote some of it down. There's some more things in there. But yeah, the moon bases thing, that kind of was surprising. Okay. All right. Anyway, so here's this. Wow. So here's, you could look at this. And of course, here's a problem. This is just sketches. This is very hard to see because we just have now. We don't have a record of what, we can see geologic history. Deep down, you can find things, fossils and stuff, different layers, right? So you can see the history of it and how things turned and so on. But the surface is this just it gets erased. There are ancient riverbeds and so on. You can find those sorts of things, but it's a little bit harder. So we don't have. Here is the last 100,000 years for this landscape. Right? We don't have an easy way of measuring that. However, let me see if I can get this to work. So here's a simulation. Does not work. Oh yeah. Wow. See how bad this is. So this was I first got this on a VHS tape. It's Bruce Shaw and Marcello Magnasco, Rockefeller. Bruce Shaw is at LDO. And this is the resolution. I mean, this is really the resolution. So they made this. I'll just show a little bit of this. They made this. So it was for Leo Kadanoff, who passed away recently. He's a very famous physicist. It's just great. Obviously, I mean, this is just great stuff. So they made this. I'm going to jump onto this. This is going to be much faster. They made this simulation. And at the time, there really was nothing like this. This is really incredible. They've got a lot of text, so let's jump over that. Right, so they made all this good stuff, right? And so it's starting to look like a network structure. I think if I can get the Grand Canyon. This is actual real data, right? So this is from digital elevation models, or DEMs, which is from satellites, right? So this is the Grand Canyon. So they're interested in, can they make this at least with a simple model? This work was never published because they just couldn't. It's interesting. They figured out they just couldn't really justify. They couldn't figure out how to write about it, I suppose. And then the computer died, and all of the code, and everything died, and they lost everything. And then a few years later, it turned out I was the only one who had one of these VHS cassettes, so I sent it back to them and rehabilitated it. But it was great work. So here's a nice example of a toy model. So this is pretty good, but this is what the landscape looks like, right? It's just like this very thin carpet. It had network properties. It looked good. So they're going to add things like there's going to be diffusion, there's going to be avalanching. So you can see this kind of avalanching. So things will fall down. There'll be an angle of repose. And it starts to get somewhere. I just want to show a few of these things. I guess I could cut this down to the right stuff. This is impressive. So it's pretty good. It's pretty good. So there's long been this debate about, well, okay, this is network-like. What do we measure about this, and how do we compare that to a real thing and say, we're in the ballpark? Visually, it kind of looks all right. Here's one where they have different erosion on different sides. But yeah, this is just lost. This is lost work. So there was a bit of a boom time in the 90s where a lot of people were making little models. I had my own ridiculous thing. But there was always this problem of, does it look like, how does it look like the real thing? And this is probably as close as anyone came at the time. It would turn out to be a hard thing to model, to make a lab model of, because no one could figure out really what sort of soil to put in, because it would sort of just wash away, right? The scales are just so wrong. But I think some people have been able to get somewhere where they can finally produce, with the right kind of potting soil, something that looks like a continental landscape. Anyway, so we moved away to actually just looking at satellite data and saying, well, let's get the description right. So that's what I'm going to do. It's pretty great. That is pretty old. Okay, so I can just tell you a few things to start this off. So drainage basin. It's just going to be, if we go to a point on landscape or go to a point on the network, so point P, it's going to be the area. If a raindrop comes like a drop falling in here, it's going to actually be plugged into this and then pass through that part of the stream. So I'm not showing in here all the divides, right? So if you walk around this landscape, there'd be a divide between these two areas. And so if we think of this again as a flood network, right? So the heart would be here, and this would be here. The pillars, so flood flows out, it branches, Very interesting, right? So it comes out quite fast, and it has to be very slow because you really want one cell at a time, basically going through a sort of diffusion because there isn't a beautiful answer to diffusion process. What I understand, no apologies. So it has to be slow, and then it has to get speedy. And we'll get to that later on. It turns out that the branching kind of changes in a nice way. There's an optimal structure called Murray's law. Beautiful thing. Okay. So, yeah, point on a stream. Basins contain basins, right? So we'll have to think about that later on. Yep, right. So we have a drainage basin on every point on the landscape. Of course, we're going to put this on a grid, which will actually just have a big matrix representing the landscape. So we'll go to each point. If you have the hill slope, right, so coming from a divide, then you can imagine that flow just sort of really just kind of comes in. So it's always like, there aren't actual channels, but you sort of imagine this linear, these little linear ones. And of course, there's subsurface flow, and that's a more complicated thing. That's a harder thing. Okay, so this is really for large-scale networks, and the kinds of things we'll look at will be continental. Right. So here are a couple of definitions. Let's talk about some of these. Okay, so here's an example basin. This is flow coming out here. So if we're at this point, if we wandered up the stream, we go up the longest one to the end of the channel. This will be the length of that longest stream. And so because streams are usually fractal, so not too much, right? There's a little bit of wiggling here, so it depends on the resolution. Right? So if you have really coarse kind of resolution of this thing, and then you refine that, smaller, this guy will get longer, right? So it's somewhat fractal. So we'll get to it later on. But here's the area then, that'll be A, will be the area of this whole basin, which is water flowing down. This is this little length here, this little stream. So there's a sub-basin here, yes? And there's a sub-basin here, and so on, right? So there's a basin at every point, and this is just sort of starting one within the bigger basin. And then there's a couple of characteristic lengths. You mentioned orienting this thing, so there's an overall, this is a Euclidean length, and then a width. We'll call it perpendicular parallel. And here are the same for this basin. So one of the things that's been sort of floating around is that there'd be, so we took red scaling instead of allometric scaling for these basins, right? So we'll get to that. The idea that there's some sort of interesting ways in which basins fit together. All right. Okay, just a reminder. So isometry, right? You rescale everything in the same way. Visually, this piece looks the same as this guy. Not how trees work, but the rescaling here is such a different dimensions or different sides of this thing gets scaled in different ways. That's of course just 2 points. It's not enough to show you that that's what's happening. But if we went out to one more, this would get skinnier and much faster. Prove that, I guess. Yeah. And so this is a good place to stop. So this will be, we'll wait in the slide, but this is the sort of the interesting thing about networks that got a lot of people, physics and geomorphology and so on, excited about it. There was some mystery of science here, which is that this length of the longest stream is scaling as the area to the edge. It's an odd way of putting it. So this is meters, this is meters squared. So if this was just dimensional analysis, this would be a half, right? This would make sense. Areas length squared length, which would be a half. This is an example of the fractalness, right? So that this length again of the stream is scaling somewhat faster than the length of the. But it's not a linear thing, so this is a bit greater than 1. And then you can combine those two together, and you get how area scales as length, the longitudinal length. Right, so this does seem to be a weak fractal scaling, 1.1. The suggestion was that this from observations in the 50s that this exponent here was not a half, but maybe a bigger 0.6. We'll get to a lot of argument about scaling. And this is known as Hack's law, after the person made the assertions about it. And if it really is greater than a half, what that means is, if you think about this, is that bigger basins are thinner, they're becoming thinner and thinner and thinner. So they're elongated, which is a little bit odd, but it may be that that's sort of happening internally and not really at the larger structure. Anyway, we'll get at actual data and we'll look at how all these things combine with each other. This is a good example of a system that has scaling laws and where we have scaling relations that connect those scaling laws together. And the usual game is that you want to have as few parameters as possible. Turns out for root networks, there's only a couple. But we'll really get into the detailed architecture of branching networks. It turns out that they're not pure hierarchies, they're mixed hierarchies, and this is true of blood networks as well. And they're very small, and you'll see it here, right? So small branches can come off large branches. It's not the sort of very simple-minded thing, big to smaller to smaller to smaller. You actually have, even the largest network will have this large stream will have tiny little streams coming in. So it turns out that's quantifiable, and that was some beautiful work done by Tokunaga. This was not really known as a Japanese guy, and it was published in Japanese journals. It wasn't really known in the US or outside of Japan, maybe for 20 or 30 years. So we'll get to that. Quite beautiful. Everything will fit together in a nice way. This is still a field where I feel like there isn't a beautiful theory, right? There's reasonable description now, we'll get that out. But this is something where we have a good sense of how things fit together from a description point of view, and I'm going to lay that out for you. But in terms of some magical theory that explains it all, I don't think it really exists. There's a lot of, this is sort of area that people get published in Nature and Science now and then, right? Because they've got their big story. But there you go. Okay, so kind of underway with complex networks. I guess I'll be over there today if you want to come by and talk. But we won't have assignments until maybe, I'll probably send one out on Thursday. I think I'll have enough stuff in front of you for you to take off. But talk about projects and think about them as becoming papers. And I'm very happy to talk about those things as soon as possible. All right. Okay. Okay, so there'll be, I know there's a little warm-up. Anyway, we're getting going in our semester, and we have fun. Right. I want to say, so we'll have an assignment, I'll send out an assignment later today. And it'll be about these branching networks things, right? And so we'll get into some more details here. But I'm not sure if I'll be able to get through everything you need to do that assignment, so the due date will be a little variable. Anyway. No office hours today. We'll start that next week. Cool. Any questions about things? I feel like I should do what no, he was that was not very nice. Favoring the one person. That was terrible. Okay. Okay, so we talked about, so this is this kind of basic idea. We have basins within basins, right? So there's every point, there's this little basin, and you can think about this could be part of, right, this could be an artery servicing some part of the body. Of course, there is this other network that's bringing all the blood back, but that's sort of the same idea. And out here we have all these little capillaries, or however we try to say that. So, various other kinds of versions of these things. Okay, so this is where we're getting to. Let me just get these variables again. So there's a characteristic lengths, right? We sort of put a rectangle around it. There's this width, which we'll call L perpendicular. L parallel, we'll just put L for that. So that's the length of the thing, sort of the length. And then there's going to be an area, which is just as you look down on it. Now, of course, there's relief here, right? The mountains and things. But we're going to be thinking about ones at continent scale. And at a continent scale, things are pretty flat, right? Mount Everest is tall, but not that tall. It's just little bumps. If you use Strava, there's a thing called Relive now, which is a website that uploads your training thing. And have you ever seen this? And you can see, this is a very important detail, but you can, it'll trace out your little run or your bike ride or whatever it is.
And it's always really disappointing because you've maybe gone up some enormous hill, but it just looks so flat. Because you just want it to let's pretend, make it by 10 in that direction. Anyway, so there are these relationships connecting them, these scaling laws, and let's see some of these stories we have. Okay, Hack's law. So this is 1957. This is based on people going out and looking and measuring things, looking at things and measuring things, which is all good. That's that paper here, and the paper was by Hack, presumably 40 graduate students who were never mentioned, in the old way that people did things, which is still done in the social sciences and other fields. Anyway, so it became known as Hack's law, and it was this relationship, so scaling fans, right? We talked a lot about scaling in pucks. That exponent h, this little h, we'll keep this as somewhere, it's sort of purportedly above a half, right? So a half is the dimensional analysis simple scaling, right? This is meters squared, this is meters, or whatever you want, to the power of a half. So that would make sense, right? So it's growing isometrically. But the claim was, at least for this small patch that Hack looked at, that it actually was scaling allometrically, which is to use that word again, and that would mean, when you think about this, that these bigger basins are kind of thinner relatively. All right. You can put a few other pieces together. There's this one. So this is the little curly L, which for latex fans, that's a /E-double-L. That makes that one, yeah. And that is scaling as the overall Euclidean length of the basin, right? Euclidean length of the basin, boop. And this is the wiggly length. That's scaling as capital L to the power of D. So that means it's a little bit fractally, right? So it's scaling a little bit faster. It's superlinear, but very, very barely, right? This is very weak scaling, possibly not something to rest on. But it just seems to be, people have seen that. It's a little bit hard to measure, to be honest. What I mean is a little bit hard to be sure if you've got, if it's 1.05 to be really sure it's statistically not 1. As we've talked about, people argue a lot about scaling, right? Okay, there was just a little Twitter outburst between some of the people's names that I've mentioned. I don't know if any of you probably didn't see this, but Duncan Watts was on there, and Vespignani and Clauset, and they were all having a little bit of a argy-bargy with each other about whose scaling laws are the best, and scale-free networks, whether they're real or not, and stuff. Oh my God. Anyway, so really not good. Twitter fights between academics, great. Okay, so, and there's another scaling. You put these things together, right? So we've got a little L here and here, the basin area here, and the overall length here. We can just equate these things and then take the exponent of the other side, and we'll have the overall length. This is a bit odd the way it's been expressed traditionally. Length as a function of area, it should be kind of the other way around, just the way it's been done, so I'm trying to connect the literature. So this is the Euclidean length, which is a bit of a rough thing to measure again, but scales as area to the h over d. So that's going to be we'll just call it 1 over d, because that would sort of make sense if we put that big D here. If that was a 2, that would be sensible, right? Area to, should scale as length squared. But again, sort of fitting with this elongation thing, it's sort of supposedly less than 2. We're going to show that at the larger scales that doesn't seem to be the case, but it's still an interesting business. Okay, so turns out there were 3 laws. There's a whole bunch of them that people have been sort of uncovering over a long period of time. I could put citations in for that too, just because that would be, yep. This is the sort of thing that happens. And so we've talked about some other kinds of examples like this, but this is it's true in biology, it's true in physics, and so they have all their names, and they're all different, and maybe not, right? So a game will be to try and connect these things to each other, right? So these could all be entirely independent. We've already seen that, on the previous slide we had, a sort of a third law connected, derived from the first 2, right? So this is this scaling of basin areas, deriving it from this one. So we know, for example, D is, what do I have? d would have been, little d over h, right? So that's a typical game, and we call these things scaling relations, where there are connections that are just simple algebraic ones, right? That's just a ratio. This d is equal to the little d divided by h. So we should be able to build up a table of those things, like this, and eventually find out that there are 2, 3, 4 independent exponents, right? That's it, and this, here it's framed in terms of river networks. This is true for blood networks as well, and of course more generally it could be about fluids, it could be whatever you want, right? So lots of systems that have scalings, there are these interconnected relationships. But these were, these all come from separate papers, people discovering, measuring things in different ways. This is, for example, like the sum of all the stream lengths, sort of a reasonable idea. Like I'm going to go to this thing, find them all, and I'm just going to sum up. I'm going to sort of measure the length of every river independently, break them all up into little pieces, add it all up, and see how that scales with area. And sort of sitting in here, and so what we're going to talk about are these guys, mostly today, and then we'll get to Tokunaga's law. These are really interesting, detailed structure pieces. I do think, to be honest, there has to be a better way to do all of this, and maybe you can think about that as we go through it. But whatever you come up with will still connect to all of these things. Let's see, so, and of course we have these power laws, right? So this is, again, if you just randomly select a point in a basin or in a big landscape, the probability that there's a basin with an area A or and a mainstream length L has a power law decay. And so all of this fits together, power laws. The paper by Cassette, actually, it just came out, was the title is something like scale-free networks are, I think, maybe it's just are rare in nature, right? Something like that. So that's, fighting words, right? And it's one of those things where I've got a whole bunch of networks that are really small, and of course they're not going to be statistically kind of anything, right? It has that whole business of, I think, when I present scaling power law size distributions you guys start with, 3 orders of magnitude is sort of this great thing to have in both dimensions. You want some, and that's just a rule of thumb, but it's like, anyway. Oh, that's so funny. All right, so so of course there are these original papers, and then there are all these measurements, yeah? And science is a little funny, so people tend to measure things that are similar to what the smart person measured before. There's real history of that. A famous example of that is, I think it's the ratio of electron charge to the mass. Does anyone know about this one? This is the early 1900s, and someone just got it wrong. Very famous character, I can't remember I need to get this story straight, but basically someone does it empirically, experimentally, and gets it wrong. They're just off. And there's a theoretical estimate, which is right, and then over time what you see is all these new measurements slowly move towards the theoretical one, right? Because they're like looking at that big smart guy. So they're like, I almost got what they got, but it's a little bit on this side, a little bit, and it drifts towards the true one. And that's physics, right? Social phenomena. Okay. Anyway, so there's a whole batch of these guys, and then, and of course these plus or minuses are a little funny, but they're interesting numbers. They're not all, a half and 2 and 3, things that we could just say come from sort of obvious ways things fit together. Oh, lights. Or do you want to sort of be in a cozy, sleepy, warm place? Like my cat. Haven't talked about the cat enough. Okay, so okay, so we're going to find out how these things are connected. Find the most fundamental descriptions, like, okay, we only need these 3 laws, everything else comes from it. We can focus on those. So then when we go to a real data set, we're going to measure those 3 things, or whatever it is, and then we'll measure it over here, and then we'll sort of collect a whole bunch, and we'll say, okay, if we want to have some, our grand theory for how all of this appears, we need to be able to produce those relationships, right? So this is, this has been around for a long time, but I still feel it's kind of, it kind of stopped at some point. So we've got a great description, and there are a bunch of theories out there, and lovely little fun models on computers, but it's still sort of waiting. Anyway, but it's still very important to understand how these things fit together, and it's quite beautiful. And as I said, the word for these is that branching networks in nature are not pure hierarchies. They're these kind of mixed hierarchical structures. Good. Ooh, I have a point. Okay. Orders of streams. Got its own tarot card. Okay. Cool. So, okay. So as I said, Horton the other day. So Robert Horton, so famous hydrologist. This is sort of the first, as I understand it, someone sort of coming up with a way of quantifying recursive structures, fractal structures. There's an improvement by Strahler, so there are these three pieces that go together. We'll get to that. It turns out that they could be collapsed again, which comes like, I guess I was sort of involved in that, but that's many years later. Okay, so you'll see this, Horton-Strahler stream ordering, and this will be used when people are talking about blood networks. They'll say we're using Horton stream ordering or something. So let's just go through. It's a simple idea. You can think of it in different ways, and I'll sort of point that out. But you can think of it as sort of iterative trimming to order these things, because we want to sort of. I mean, one thing we want to say is like, you could go here and measure the width of this thing and sort of have this very fine-grained idea of it. The problem with, say, that probability distribution that decays like a power law, it doesn't tell you if you just handed that, right? There's a probability of stream length decays like a power law. It doesn't tell you anything about how these things fit together, right? There's no structure in that thing. So we need to sort of understand, like these are kind of clearly small ones, so we want to signify that by some sort of labeling, some sort of quantification of that, and then and there's a bigger main one in the middle. So how do we do that? So the blood network version would be a capillary, but out in actual landscape, you can go and say this is where a channel starts, right? You can actually do that, and if you have fine enough topographic data, then you can do similar sorts of things. So you can do it by remote sensing. Once again, every science changes, right, as you go from data scarce to data rich, right? So once you get to remote sensing, then you can do all sorts of interesting things and potentially bad things. But that's what's happened to many sciences now. Okay, so a channel head, so we have that, and then we'll talk about a source stream. These are just sort of words. So a source stream will be one that starts with you go to the landscape, this will be kind of smooth or messy or whatever it is, but there's no well-defined channels in here, and water's sort of coming in, and then boom, there's clearly like flow here, right? So we'll call these little dash ones will be source streams, and then we want to say, well, where they hit each other, that's going to be a next kind of stream. That's a different stream. And so we're going to use omega to label stream order, so that's this little guy is going to appear a lot. And so this is a funny thing to think about. So these are, I'll show you how to do it, but these will be order 1 streams, these little dash ones. These will be order 2 ones, and this will be an order 3 one in the middle, and then that would keep going. You can see this is kind of growing exponentially, right? So these are very small. The next, this sort of factors getting bigger and bigger by a certain factor. So you don't have order 53 networks, right? So depending on your resolution, the Mississippi might be an order 13 or 14 stream because these things grow exponentially. Laura? Yeah, so that's right. So that's going to be this mixed hierarchy thing, and we'll get it in the next plots. But these are order 1s, and this is a little bit thicker if you can see it. This is an order 3, and we'll get it on the next slides. But yeah, exactly, right? So this is this mixed hierarchy idea. So even whatever the largest order is in the network, it will have order 1s and 2s and 3s. And this is this work by Tokunaga that came later, that where he showed there's actually a really nice structure there. So it's quite beautiful how all this works, I have to say. That might be somewhat limited in blood networks, but it's actually still broadly true, right? That there are, yeah. Okay, I'm putting all the things up. Okay, so we're going to start with this and say, let's label all of these, obvious incipient streams, right? These ones that clearly have a starting point. We're going to label them as order 1, and then we'll trim them off, right? So you just take your thing, you trim them off. So now we're left with this picture, and then we'll just do it again, right? So it's a recursive iterative thing. These will be now these look like our new order 1 ones, but we'll call them order 2 because we've taken a step, and then we'll trim them off. And we'll be left with this one, right? So this will be order 3. And then we just keep going and keep going and keep going. All right, so that's one way to think about it. You can see that as a result of how this works, that just as you say, right, so order 1s can be absorbed, so we'll sort of use that language, it'll be absorbed by an order 3 here. That's an order 1. But there are all these order 1s that they hit each other, right? So it's an order 1 hitting an order 1, and that makes an order 2. So that's a repeated kind of structure. Now, of course, this is presuming you have a network that just has bifurcations in it, which is fair, right? Just river forks. This is a bit confusing. Like, so in Pittsburgh, which I should understand, my wife's from there. So the 3 rivers thing, is that just because there are 3 names? But it's a fork, right? It's not like there are 3 rivers that hit each other. Because that seems like sort of a weird geomorphology thing, but it's actually just, right. They just changed the names. Oh, so it's really 2 rivers with another. I think it's in China. There are 3 very large rivers that really do actually kind of parallel each other. It's strange. It's sort of a strange structure, but generally, this sort of thing happens. All right. So this iterative thing, and that's not actually necessarily how it was approached or sort of described in the first place, and I'll describe it in a different way. But you can see what it means is that, you actually need you can imagine these 2 hit each other. You can think of it as like they then turn into an order 2, or they make an order 2. So an order 2 starts because 2 order 1s hit each other. And that's the same up here at the next level, right? So this order 3 is starting because 2 order 2s have hit each other. So fair enough. So you need, for every order omega 1, you're going to have 2 order omega minus 1 streams that have hit each other to start it. And then you'll have these side omega, well, this is say order 7, you'll have side streams of order 6, 5, 4, 3, 2, 1. Okay? And there'll be more and more of the smaller ones, right? So that's going to have its own little scaling thing as well. And that's Tokunaga's law. Seem okay? So it's not supposed to be a crazy hard thing, but some little bit of, what it leads to is just a little bit of counting sort of stuff, right? Some sums and things, trying to figure out some stuff, which is fun. Fun, combinatory to people. Yes?
Would you need to define the size of like an order 1 in order to continue
Right.
defining the sizes of the hierarchical?
Yeah, so now we've got labels and we can say, what's the average length of an order 3 one, right? And so there will be 2 parts to it. One is, this is a stream segment. We just go to where it sort of stops. Or we could go all the way up, like you would sort of if you're in a boat and you're just trying to take you take the main river. As you come to every fork, you go up the main river. So that will be that little curly L. So we have those measures, and then there's the area, right? So that's all still there as well. But of course, it's distributional, and that's something we won't really get to too much. I'll tell you about a little, but as you go across a big landscape, there are order 3s of all kinds of sizes, and that has its own special kind of distribution. But it's enough to start with to look at the average lengths and the average areas. Is that okay? Yeah, exactly, right? But this way of labeling things gives you a way to then start describing the landscape properly. But I just want you to have in the back of your mind that there could be a better way to do this, right? And so, you might want to start from this end, right? So you might want to start from the A order and kind of go out from there. That feels like a more natural way to label it. And if you have resolution problems, right, this is, there's actually really 2 order 1s here. This is really an order 2. So there's a bit of an oddness there in terms of resolution, right? So, and that's very much, because it's fractal, it doesn't really matter, but there's sort of this unsettling feeling that if you have, back in the 90s, we had satellite data, which was a mile resolution or a kilometer resolution, depending on who was in charge, I suppose. And now it's, 30 centimeters or something, right? It's very refined, yeah. But clearly, when you go from a mile to 30 centimeters, you've changed units, of course, but you will be getting much more structure in here, and does that affect this description in a way that's upsetting, right? Does this turn out to be an order 4, and this is an order 3? That's sort of a bit upsetting. Okay. Anyways, see if you can think of a different way to describe the architecture of these networks, right? That's what we're trying to do. What's the architecture of these networks? And we're starting this course with pretty physical things, and we'll move to more madness later on. But we know this thing sits in space. That's good, right? Blood networks are in 3 dimensions. That's going to matter. This is really in a 2-dimensional space. That's going to matter as well. These things, of course, can get deeper, right? As more water comes in, that's less. We've got to keep the whole thing inside the body, so that's going to be something that will matter later on too. All right. So if this is just all you were handed, you would actually say this whole basin is order, and we'll use a capital omega 3, right? So this is just sort of a notation thing. Okay. So this is the Mississippi. This is using a mile resolution data set for the U.S. Of course, Lake Champlain, which is over here, goes to the north, right? Flows out to the north, which is a bit unusual, I think, for most of the drainage in the U.S. is typically going and being consumed by Southern California, Chinatown. Okay. Is that what it's called, the movie? No one knows this movie. Great movie. Yeah, Chinatown, right? Yeah. Right. It's a great, incredible movie, right? But, right, so the LA Water Department went out and bought all the little aqueducts or whatever, aquifers, right? You just see it on a map. You see this little LA water. I mean, there were places that had paddle steamers. What's that place out in the east of California? Paddle steamers and so on, right? I mean, and they're just salt plains now, yeah. Very nice gardens in LA, because that's just natural. Okay, so this is only the top orders. Obviously, this would be a big mess if we tried to show them all, but at that resolution, you end up with this one being order 11, the trunk of it, right? And so here we're down in, the bottom of the US. And then these colors, which are just brutalist, green screeny type colors, evolved things since then. This is what you should not do. This is terrible, right? Okay, it's absolutely awful. Yeah. It's like my youngest daughter said, she told me that design didn't exist in the 1990s. And I'm like, what are you talking about? And she looked at some websites, I think, that were from the 1990s. Like, people just didn't know how to do it, at all. Apparently until the turn of the century, no one could design anything. Like bridges, anything, houses, whatever. Okay, so it was pretty damning. So, but you can see there's actually a lot of fluctuations here in terms of length, right? So these are 2 quite small order 8 ones. So that's something to worry about when we're trying to describe this architecture. We've got a lot of variation, because you'd sort of think the order 8 ones have to be much bigger than the order 7 ones and so on. But actually, it's pretty variable. So this description is going to work very well. It gets a long way, but I still feel like we could do a much better job. Yeah. Anyway, so actually what is hard to see here, so there's the order 11. The order 10, there's an order 10. You can't see it at this resolution, but here are 2 order 9s. They make an order 10, and it's super short because it runs straight into another order 10 and makes an order 11. So you'll see these repeated connections, right? So here are 2 order, what are these, 8s? They make a 9. 2 order 8s, they make a 9. These are side branches, right? 2 order 8s make a 9. And then these 2 9s are making a 10 here. That's the start of that one. And this 10 can have side branches of order 8, 9, and 10, and so on. Yeah. Say it again. Yeah, so the order, okay, so that's good. All right, so the order, we've made you can imagine sort of making, right? So this is 2 8s making a 9, right? This will only increase when it hits another, only lead to an increase when it hits another 9. So it has to hit another 9. If it hits anything of a higher order, it's absorbed. So you could think of these as sort of generator streams, and then so a stream can be a generator if it hits another of its same kind, or it can be absorbed. So here this one's absorbed. And here's absorbed, and here is absorbed, right? So this one has 3 side streams of the, right? This is order 10, these are order 9. So this order 10 has 3 side streams that are 1 order less. So that's pretty a typical kind of number, actually, 2 to 4. But then, and it's not really shown here, as you go down to the next order, you have like a ratio more, maybe twice as many, roughly. And then the next order down be twice again. So, it's not really showing you, but there's a lot of, it really is sort of clearer here, right? So this is a small one, but this is order 3. This is an order 2 here and order 2 here, so they're absorbed, they're side streams. Here are the 2 order 2s that make that 3. So here are the generators, these are absorbed. But then if you go and look at the order 1s, it's got 1, 2, 3, 4, 5, 6, 7, 8. No, it's got a lot of these little guys in here. Yeah. And then if we had another level, right, so this turned out to be, these were really order 2s, and this is the order 1s here, there'd be a lot more of little order 1s in here. Yeah. Right, so the only way, as you're sort of going down, you know you're on an order 7, you have to hit an order 7, and then you know you'll be in order 8. If you hit anything higher than order 7, you just stop, and you just become that part of, yeah. Yep. Okay. So this is, this took decades for people to sort of figure out, and like, how do we classify this? And as you can see, it is still problematic in that these things aren't sort of characteristically similar in size. And this I think I've basically said all this, but here's the idea, right? So you could do this in another way. You just label the source streams as order omega equals 1, and then follow them down and do this thing we've just talked about, right? So when 2 1s hit each other, that's a 2. If a 1 hits anything greater than a 1, it just gets absorbed. But in general, when 2 streams of the same order omega hit each other, then now you've got a stream of order omega plus 1. And that's it. And if they're, and you can sort of write down like this, right? So the order of the new stream when there's a merge, so an omega 1 stream hits an omega 2, then the order of the thing that the next stream will be the max of them, right? Plus this little Kronecker delta, if we want to write it down, right? So Kronecker delta is 0 if these 2 numbers are different, and 1 if they're the same, right? Because it's awesome. This little indicator, right? This is the identity matrix, basically. This little indicator guy. Okay, so if they're the same, right? Same. So max is just, right, going to be omega. The omega 1 and omega 2 are the same. Then we get a plus 1 here. And if they're not, you just take the max and yeah. So you can write it down like that. So we have a plan, and I kind of wanted to go through it so we make sure we understand it, because then we have to do a bunch of calculations. If we want to then say, what's the area of this basin, this order, 11-1, given we know what the areas of order 10s and 9s and 8, so we have to sort of fit that together. Yeah. Cool beans? Yeah. So, as I said, resolution of data messes with the ordering, right? So if we get finer and finer data, the orders will increase. They should if we really move in. But the relationships are going to be robust. So what you, of course, can do is say, here's my data, right? I have my digital elevation model of a landscape. I find all the streams. And then compute all these things, these orders and so on, and label them. Then you could make a coarser version, right? So you could average it. You could make your version worse and see how it changes in that direction. Or you could wait 10 years for technology to get better and go the other way. Yeah. I don't know what the full map of the US now would be. USGS, the Geological Society, you can just download stuff, which is cool. Right, so we've discretized the network, we've broken up the little pieces so we can try to understand the architecture. Yeah? Cool. All right. Good. Cool. So there are a couple of things, and so this is Peter's question really. So now we've got this labeling. So we've got some basin of order omega, then it's going to have within it, right, we're going to label it like this, and this is sort of in keeping with the literature to some extent. There are going to be n streams of order little omega. The way this works is there are more of the little ones, right? So as you go up in order, you have less of them, right? So there's only going to be one stream of the overall basin order. So if it's an order 7 basin, there'll be one of order 7 stream. There'll be more order 6s, more order 5s, more order 4s, right? Okay. And then we'll have area, which is right there as A omega, and we'll have a mainstream length, which will be, right, so we'll start here and we'll travel all the way up. So we're actually going to add together different orders. So maybe it's this, right? So we'd sort of find the longest stream in the whole thing, and that will be it. But we're going to say these things are stream segments, so this will actually be an order. This is an order 3, this is an order 2, and this is an order 1. So we're adding them up. And we'll say stream segment for that. So there's sort of another length that we'll think about here. And we might be interested in how those things scale as well. Yeah, right. So the stream segment, like this is the only part that's order 3, and that's got a length S sub omega. This has a length, it's S sub 3, this is length S sub 2, this is length S sub 1. Okay. Yeah. Okay? Okay? Is that okay? It's okay. Maybe okay. Okay, so laws of branching. All right, so this is Horton's laws, right? And so this is Horton. Schum as well, and Strahler got involved as well. All right. So this is sort of the stated thing. Now, of course, it's a little rougher, and I'll show you examples, but this is the idea. And it's framed in a way that these numbers are all greater than 1. So the numbers, as you go down in order, you get a factor, a certain factor, and we're going to write as R sub n, more streams, right? So if we have, and this is typically around 4, right? So it's just sort of a funny thing to think about, right? I don't know what it would be in 3 dimensions or so, right? I mean, we have to think about, it's not obvious straight away what that should be if you have a blood network, but what's this, where is this 4-ness coming from? And this is one of these games where people will say everything is the same, and then there's also people saying, well, it's all a little bit different and it matters, and yeah. But roughly there's a lot of measurements around 4. Yeah, there's stuff sitting here for people to work out. So these are actual numbers, right? You're going to count these up. So these are explicit numbers. When we get to something like stream lengths, these bars here will indicate averages. I know I often use angle brackets, but it's sort of a bit of a mess in all of this. Anyway, so these are, it might flip to that, but these are averages. So and it's framed in a different way, right? This is omega plus 1 here, right? So 7 and 8, and this might be 8 and 7. So as we go up in order, we get to bigger and bigger streams, right? We're getting to the scale of the basin. So the average size of these guys is, divided by the average size of the ones below in order is, again, some ratio. And the claim is, this is basically constant. And you can imagine this will be a little bit wrong at the ends, right? And there'll be 2 reasons. At one end, you've got the smallest streams, and you've got issues with resolution and measuring them. And at the other, you've just got 1, right? You've got 1, and then you don't have enough statistics. And that's a thing to look at as well. Okay, so this is typically around 2. I'll give you that. And then this was also floating around as well. So there's this one, and this is for area. And this is typically around 4. And actually, from a sort of, if you go through and assume everything is beautiful and connected, this is something we're able to show that these two ratios are actually the same number. So that's something to get to, which is a nice connection. So this is one of these things where we start reducing pieces, but for about 50 years, 40 years, people weren't really sure about that. 50 years, yeah. There's this whole literature of people slowly connecting things together. Does it make sense? So these are framed slightly differently, right? Omega plus 1 omega, omega plus 1 omega, omega, omega plus 1. So these are these laws of the universe sort of statement thing, beautiful things. Physicists come along and say, I can make that happen. And then everyone argues, and it's not really true. So we'll see. Okay. Let's look at how this works. So these three laws, we've got these three parameters that we could measure for a landscape. And you might be worried about how that landscape changes, right? I mean, if you had all of, say, Asia, that's a lot of very different kinds of climates and regions, so be a little bit thoughtful about that. But it seems to be reasonable to look at something like, the Mississippi, even so, right? Or the Amazon and so on, right? These are just good, big, coherent basins. All right. So, simple thing, and this is just, marching it out in a very painful way, I suppose, but the number of streams of order 8 is going to be the number of streams of order 7 divided by this number, right? So this is typically around 4. So we're reducing, divided by 16. And eventually we get down to the number of streams of order 1. And if we think about, right, so I like to always do these things. So we start off, we know what this is, right? And then we decrement it a little bit. So we've got a squared here. This is to the power of 1. I don't know how you do this. But this is, if you add these two guys together, then they cancel. So you're going to get to n1, and then we need to be down to omega minus 1 by that point, right? Because 1 plus omega minus 1 is omega. And that's what these things are adding up to. Right, you have to concentrate sometimes. You're decrementing, and this is one of these things where you have to concentrate a little bit. Like how many numbers are there between 7 and 4, right? There's always, I think, I don't know. You have to stop a little bit. Okay, this is a ratio, right? That's with a power, and of course we can write that more usefully as what it really is, which is an exponential. The omega minus 1 is sitting here, so this is e to the minus log n of r, right? This is on the bottom. This is 1 over Rn to the omega minus 1, right? So this is Rn to the, I know this is a simple thing, but it's just good to do. So we've got this. So this is our power. So then we'd want to write this number is great. This is greater than 1, so that's sort of an important thing. And we can write that as e to the ln of Rn, as you can for any quantity. And then we've got this power omega minus 1. So this is e to the minus 1 ln of Rn. Always good to do this, I think. We like exponentials. Exponentials are groovy. E is a pretty good character. And then, so it's e, this is a positive number, this is a positive number because this was greater than 1, right? So always good to do that. I think that was something, greater than, this is greater than 1, so this is greater than 0, this is greater than 0. I can't sort of say strongly enough how important it is to structure things so that it's clear that there's a negative or whatever involved, right? You really need to do it. If you've written something out and it's got some parameters and so on, and kind of rough that this will always be positive, because sure, we could leave this as 1 over Rn. We could do that, right? But it's we're misleading. We're leaving open the. This is a simple example, but obviously as you get to more and more complicated things, always good to express it in a way that's kind of clear. That this is a negative, this is e to a negative power, right? So it's a decaying thing. Yeah. So this is decaying as we increase through orders. But it's decaying exponentially, right? So boom, 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 really dying away. So same story for area and length, but these are pluses now because it's flipped around, right? So the areas are growing, the lengths are growing, so they're growing exponentially. You can start to see from that so numbers dropping and the area and length increase, you can start to see how that might give rise to these power law size distributions, right? Because you get this is a big growing kind of system, right? Lots of tiny little things, and then they make slightly bigger things, but those bigger things are bigger by a factor and bigger by another factor, and right. So that means that we move through, even though we might move through 10 orders, we'll move through, from the start of the Amazon, like tiny little things in the Amazon to the overall Amazon. It's a huge range of length scales, right? So not to be deceived by, having order 11 basin. That's a huge thing, right? Because you've got 4 to the power of 11 or 4 to the power of 10 and 2 to the power of 10 are the numbers that are really appearing. Yeah. So you should think of, just like you would with earthquakes or whatever, the orders are logarithmic objects, right? Yeah. So order 5 is not just +1 relative to order 4, it's a factor bigger. So these are laws of averages. As I said, I'll touch on this, a lot of painstaking work to say, well, let's look at the distributions of those things and then connect them, which is a really nice thing to do. And then averaging for, the numbers, right, so if you have some basin, you just count all of them. But if you have more basin, if we have a basin 7, order 7, another basin of order 7, and then a whole bunch of them, then you can average, right? You could say, well, how many order 1 streams are there in this one, and how many order 1 streams? So you could do that, but it's really averages. Averaging is built in with one basin, right? So this is within a basin, we have averaging of stream lengths and areas. Okay, right. So this gives us a lot of how things fit together, but it doesn't, I think and you can see the way people have calculated things over decades, they kind of start with Horton's laws and then they sort of proceed as if it's a pure branching structure, right? Because you've got an order 7 basin, and now you've got say a Horton ratio of 4 for number. Okay, now we have 4 order 6s, and then they're fed by 5s, and they're fed by 4s, and they're fed by 3s. So you can imagine this sort of branching thing. Okay. There's another piece in here, which is the stream segment lengths, right? So how does this length compare to this length, compare to this length on average? So that's another one, right? And in fact, you can show that these things have to be the same, that the Horton ratio for stream segment length and length. So that's a little problem to work on. It's a small one. It's a nice little one. It just means that you understand how these things are fitting together. Very small. So here are some examples. Right. Okay, good. And these get you the orders of magnitude. So here's the stream order across here, right, from 1 to 11 in this case. They're all 11s actually. No, actually 10, just 10 here. And so Mississippi, the Nile, and the Amazon. And so this is the number going here. This is area, which is increasing faster. Length doesn't grow quite as fast because, of course, it's, this is length squared. This is area, just length. This is, in this one, this is the mainstream length. This is the stream segment length. So you can see they're scaling very similarly. So the ratio for these guys is the same as the idea. The ratio for this one, which is decreasing, the ratio for this one is increasing. I claim that they're the same. So that's something to get to later on. You see some deviations as you get to the ends. That makes sense, right? Again, sort of just one, some funny things might happen. There could be geological constraints. You only have one example. So the numbers that go into each of these data points, there are many, right? So you're counting a lot here, but then you're averaging over many, 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 but increasingly less, right? This is the number you're averaging over. It's decaying, and it gets to 1. There's only one longest basin, longest stream, and largest basin. But the point to look at this is, how we do our power laws, right? Like, hold up a rule, it's not bad, right? It's not bad. It's not doing something totally weird. It's sort of, but it's going to be a little messy measuring it because, maybe you want to get rid of this one, you want to get rid of this one, and yeah. So trying to find some, yes? Yeah, so that's another piece, and I'll show you some stuff later on, but the variance, so if you say the stream segment length things, these actually have an exponential distribution, right? It's not a peak distribution out here, it's actually, so it really decays. And so you can sort of you start to put all these things together because eventually you have to add up to some power law size distribution. So you sort of have all these little things, there's lots of convolutions of distributions, messy, crazy thing. But the variances are huge, yeah. And so they're really masked by this sort of focus on just the average, yeah. And then we saw I think in the example for the Mississippi, the actual thing, there are some tiny, there's one you couldn't even see, right? There's an order 10 you couldn't even see, yeah. Yes, so slope, and I'll show you something with some nice work done the last couple of years. But the slope, there's a very odd, there's sort of this rough empirical connection between slope and the drainage area. But it's such a messy thing. There are a few of these things floating around where it's just like, we just give it some exponent. People have definitely tried to do it. It's at that larger scales, right? Slope sort of is pretty, it's not really there. But in terms of making a model, you need it. Yeah, so that's a whole other thing. I don't think anyone's going close to modeling it at that big scale. And there's also just the real details of erosion are weird, right? So, a particle gets up into the stream, and we talked about a little bit in parks, like there's a parallel size distribution for where it lands. There are, specific words. What is it? Not catapulting. What's the right word? Anyway, of how these particles will jump around and how they actually rotate in the fluids. It's also a weird issue. Depending if they're like elongated little boxes, then they tend to rotate in weird ways. It's right. So there are horrible details, but you sort of want to be able to make something that doesn't matter. It's interesting. There are the toy model versions. I don't think there's a really good, super sophisticated, insane model. It's sort of still at the toy model.
We have a couple of hydrodynamic models. The EPA has a couple of hydrodynamic models, so they try and model just like
For a channel?
and like branching channels.
Yeah, sure, absolutely. Yeah.
And
But like,
crazy, and they take like these massive clusters of models.
right, just to do a really good, right? Do that really well, but not
Not like the entire country.
right.
They're like doing payments and tributaries.
Yes, it's incredibly important. Yeah. I mean, it's such a big deal, right? I mean, and so Houston, in terms of people thinking about wetlands and those sorts of things, right? I guess in the last 10 years, they've filled in a lot of places that absorbed water. I mean, when you start to build urban areas with concrete, you really change what's possible. But that's another whole bunch of stuff. And we have people here that work on that sort of thing too. Subsurface flow is such a big deal, like how much gets stuck underneath. In many ways, it's sort of it's not simplistic, but it's sort of the big picture view, right? So these things hold for cardiovascular networks. It's true that measuring these networks is a little messy, right? But you read these papers, and there's various approaches to doing this. I think there's one where they took the rat involved and filled it up with plastic and then removed the rat, basically. So then you just have the whole cardiovascular network. The rat has demised, but there's also just getting out. Here are some like sploof, here's some blood networks, and then they're sort of counting it and stuff. And it's a section, so there's a lot of that, right? Here's the pulmonary tree, something like that. But getting the whole system is hard, and it's different in different places. There are some, We're going to get to metabolism later on, as I mentioned, which is all connected to this network story, because you think of organisms, we have this really fundamental thing inside us, which we have networks delivering nutrients, right, and taking them away. We have a couple of different systems for that. But we're three-dimensional things with sources for the energy that then has to be distributed out by a network structure, or is. That's not true for the smallest things. I think insects have just diffusion and stuff, right? And cells run on diffusion and so on. But there, certainly, So the experiments there to figure out how much oomph an organism has is things where you can actually try to count up measure the mitochondria, basically, which usually involves atomizing the organism in question. So a little chart remains of a squirrel, and then you separate out those bits. Which is a bit like taking your food and it has this many carbohydrates and this many quarks and that sort of stuff. And it's like, but it's apple pie, it's delicious. Mm-hmm. All right. Okay, but this has been done, and so this takes a while. Not a remote sensing thing, right? This is messy biology. But we should be able to, you would think, eventually with fMRI, right, if it gets, I don't know what the upper limits possibly are for those sorts of things, but we should be able to put an organism in and just go and get a picture of the whole thing, right? Yeah. And then release it back into the wild. There's very confused dreams about cylinders and stuff like that. Okay. So here are some statistics. Wow, it's taking me a while to get through it. This is a paper we're going to come back to about metabolism. It's pretty famous, and so we can just sort of ignore these things. But these are for organisms. A couple of people who hopefully volunteered have had their numbers measured as well. Bit of variation, right? So there's some interesting variation here. And so if we look at, say, this is a branching ratio, right, for the number. Not so many. It's somewhat. I said 4 actually for river networks. It's less than 3 here. There's some similarity for pigs, and but of course these are just 3 samples, and these are just 3 sub-networks. Dogs have been involved. Again, this is not good. But these seem to be, within species, it seems to be pretty similar. And I think the story I came to eventually is that branching networks are good for doing things, right? But in terms of like organisms making them for themselves as you grow, and for us it's like angiogenesis, which is pretty interesting. You have to think about how does a blood network grow, because it actually is this loop structure, right? So how does that keep getting bigger? People have studied that and made models of it. It's an interesting thing. Is that you can have different solutions to that problem, right? So this is a higher branching ratio than us. And rats are a low one, but you are taking a point source, or it's a big blob, but it's a sort of a point source in space, and then sending a network out from it. And as long as it branches in a kind of a fractal way, that's going to be okay. As long as it's not too slow, not too fast. But this is easy to implement algorithmically, right? From a growing point of view. It's like just branch now. Trees are the same, right? Branch. Of course, for trees, we have phyllotaxis, which is a whole beautiful thing, and Fibonacci numbers and stuff. That doesn't seem to be in here. Huh. Okay, I should add that. Yeah. Pigs and humans, right? We have some good similarities. Pheromones apparently are similar, which is complicating. Yeah. And I guess the organs go this way. Presumably they could go that way, but we're in charge. So thank you for that, kidney. What do we have? Hearts, livers? Someone running around with a pig heart? Heart valves? And we don't reject them. Sort of ironic that you might then eat some delicious bacon and like mess the valve. Thank you, pig, for both of the things. You delicious, unfortunate animal. Oh, sorry. I never really. That's true, right? I mean, yeah. How did you get that thing blocked up? Well, awkward conversation with Wilbur. Yeah. Okay. So, really a bad thing to make animals talk and like anthropomorphize. It just really complicates things. There's an old Howard Jones song. Howard Jones. No one. Nothing. 80s. English, but it's something like farmyard favorites, like kids' books. At the table in a different disguise. Some line in there like that. It's really ridiculous. Okay, because you do have to have tricky conversations with kids at some point, right? It's like, okay, so we do it. We're good at it. There's the Santa thing. All right, so. Okay, so here is a bit of a range for these things. This is for actually going back to river network numbers. Bit of a mess. There's no explanation for these exactly. They don't explain how. So they tell us how these things go from level to level. We're not really sure where they come from. Why those numbers are the way they are. They don't actually explain how these things are structured, and that is going to be where I'm going to have to start on Tuesday. We'll get there. We're going to get there. But I just want to tell you a little bit now. The first paper is 68, so Horton is 45. Right, so it's 23 years later. It's in Japanese. It has a little English, so you can link to these if you want. There's a little English summary, I think, in all of them, maybe less than a page. But Tokunaga had gotten hold of Horton's work and said, this isn't quite enough, right? Because it doesn't tell you, so I know how long these streams are on average. I could make sort of an average one of these things, but I don't know how many little side streams there are. So he really gets at the architecture of this, and if I can just sort of lay out what these things are, and we'll talk about it properly on Tuesday. So it's a new parameter, so it's going to be T for Tokunaga, so it's going to be mu. It's just ridiculously another set of labels for orders. It could be omega 1, omega 2 if you want. But this is going to be side streams for an order mu, right? Enter as tributaries into an order omega. Right? So this could be order 10, and these are the order 7s. And so T 10 7 would be how many order 7 streams on average go into an order 10 side. So there'll be two 9s make it 10, and then there'll be order 9s that come inside, 8s, order 7s, order 6s, all the way down to order 1s. And this tells you you can get even more detailed if you're insane after this. But the idea is this basically this does a better job of telling how these things fit together. Right? Because now we're going to actually know we'll have an estimate, sort of a sense of how the scaling goes for these side streams. So you're always going to have order mu stream is generated by two order mu minus, right? So they come together. So these twos make three. And then, as I said before, there are two twos coming in from the side. So let's say for this, if that held true across the landscape on average, and so this is going to be an average quantity, then T32 would be 2. But this could be 2.34, right? Some average number of streams. Okay, so, and I just want to show you, and we'll get to it again, is that this turns out to have a nice scaling, right? So there's T1, which will be, if you have an order 8, this is the typical number of order 7s, right? So it's just one below. The point is quickly to say this, it just depends on the difference between them. So the number of 4s going into a 7 is on average going to be the same as the number, so it's a difference of 3, as 7s going into 10s, right? Because it's a fractal thing, scaling thing. So that's a reasonable thing just to say. It's actually true if you look at it, but that's a reasonable thing to say. And then it turns out that these things scale as well in a nice way. So if we have, say, 2 streams coming in, side streams, of the next order down, then there's going to be some ratio here, and we have to figure that out, which just increases the number, right? As we go down, as we increase the distance, the difference in order between our stream and these side streams. All right, so this is going to be another law which is observed, and then we should be able to fit everything together. But this becomes the one that we can start with and then derive everything else from, which is very nice. And Tokunaga figured that out. I remember coming across his work. Don Turcotte, who's a very famous scientist. He's now at Davis. He was at Cornell for a long time. He presented some stuff on it, maybe in the 95, 96 at Santa Fe, saying no one knows about this in the US. It's a big deal. And anyway, but people have actually done this for blood networks as well, which is quite detailed work, but they've been able to show that even this holds up there as well. Okay, so that's more stuff about branching networks. I'll put out an assignment, but obviously we have to talk some more. Thank you. Fun times. Alrighty, so I think we can start. So I hope you guys didn't go splat on the ice this morning. That was pretty bad / interesting. Anyway, good day for studded ties, right? Yeah. Okay, so we're going to talk more about this branching network stuff, and I guess I want to emphasize that it's a big deal, right? I mean, this is the dominant sort of structure on the Earth if you look at it from space. The actual geomorphological structure, that is. And it matters tremendously. Rivers are a big deal for us. And then, of course, the branching networks inside us are pretty important things. Keeps us sort of running around, so we need to know about those things. So in the I guess I'll call them supply networks, but it's optimal supply networks, right? That'll be a sort of a next section. So we're going to sort of describe these things and then eventually start to talk about, how efficient are they, how well put together are the networks we see around us. Okay, so I did a few little drawings because I want to explain some basics about how you might go about deriving, from just from a satellite image, how that gets. I'm just going to talk about how this works, how that gets transformed into basically a matrix, and then you have to figure out how to extract the networks from that, right? So there are some harder things too. If you have, say, a picture of maybe the tidal areas, right? That's a bit harder because things get wider and so on. So you want to, you need to use some image recognition techniques to kind of map out the shapes because you're really worried about the width of the rivers and so on. That's also true of some of the imaging for blood networks, right? So that's just a hard thing to do well because you're going to end up with this 3D, right? Reconstruction of a network, and then you have to sort of think about how you're going to go in there and we talked about stream ordering, so I will go through that a little bit again, but how do you do that for those networks? And I mean this in a computational way, right? So the way that's been done, that's the data I've presented to you has been by people actually getting the goop out on a table and counting things, right? So that's laborious, right? But we want to get imaging of 1 million people and here are all these networks inside them, and so let's do it fast. That's how you transform sciences. Okay, so I'm going to talk about that a little bit. I have just a couple of things. So I did have some hiccups with the assignments, so I'm sorry about that. It took a while to get them to link to to have the assignments online, but they're here, and they're due a week from Friday, right? There are the usual ridiculous references to things, but basically this is assignment 1 and assignment 2. There's some data sets involved. You can find them in the PDF, or well, no, I haven't put them there. It's in the PDF. What have I done? Yeah, okay. So it could be a Ron Swanson theme. We'll see. That could all get changed. What's that? They may be, yeah. There's no shortage. You do want something that carries you all the way through. I mean, if we look at some I will. If we go back here, so I think Coconut's back here. This was season 7. The theme was Monty Python, which was quite enjoyable. Right. So these are fun. The pantomime horse. This is really for ecologists. This is really enjoyable, right? There's a Jacques Cousteau who fights off an ant or something like that. Very strange. On land. Anyway, so yeah, these are really magnificent. I mean, this thing about aqueducts, wow, unbelievable. All right, anyway, so you want them to be thematically solid, obviously. All right, so those things are there. I am going to work on obviously some weird glitches there. I'm not sure what happened to that, but the way I do this, I'm going to, I know what it is. Symbolic links. Okay, so I'm going to do a better job, I think, of like breaking up these things that are recorded here, for better or worse, and just repackaging them a little bit better. And they're just sort of historical things. That's random. Okay, Pratchett is here. He's always our neural reboot character. The punning, very strong. For those of you unfamiliar, Pratchett is a assistant director of the course. The Towering Inferno, it's just hilarious. Okay, all right. Yeah. Oh my God, it's too easy. Anyway, basically the greatest cat in the world, except for all the other cats. Sorry. Okay. All right. So hopefully you've been able to find assignments. We're going to have office hours really straight after this class today. They'll kind of move around a little bit, but they'll be on Tuesdays and Thursdays back over at Farrell. There's a meeting at 11 for what is being called Story Wrangler, which is our effort to extract stories from social media. So the office hours will firm up as we go along. All right. Okay, let me get the right thing. So I just added these to a sandbox. So let me talk about, yeah, okay, all right. This is good. This is not a bad order to do it. So this is this tiny little landscape, right? It's a 5 by 5. I thought we could work through this. And you've derived this network, right? And so you can see this. So this, might be a mile resolution or something ridiculous, and we're on the, the contiguous U.S. or whatever, the northern North America. So it's a bit of a funny thing to do, and you can imagine. We talked about this issue of having better and better resolution. It will change these structures, but this is really what you do with a satellite image. And I'll get to how we actually get this next. But you can allow different things. So you could say it's only going to flow to the nearest neighbors, right? So we could do that, the 4 nearest neighbors. Or we could allow this as well, and then there's a square root of 2 that we're going to worry about as well. But let's say this has been derived. Then, so once you've got this network, you want to make a little algorithm that will do the stream ordering and find basin areas and so on. And this will recur in a couple of places. So I've got the example here, and I thought maybe, let's see if I can show some components here. It'll be interesting. So we've got this one. I'll make this bigger. There you go. Okay. Seems dangerous. Why is it doing that? Just do that. All right, okay. It's a bit odd. I'm not sure it can handle the resolution. Okay. So, it's exploded again. So this is our, I know what to do. How do I do that? It's, nope, all right. Nope, okay, fine. Make this bigger. So this thing, okay. All right, so let's imagine, so stream ordering would be something like this, right? So you come along here and, let's use blue. It was a good color. So we'd say, this is this thing we talked about the other day, right? So we go to all these source streams and we label them as 1s, right? So these will all be 1s. So you'd have a little algorithm that has to do that, right? It has to go to a place and say, there are no other incipient things, and I'm going to label all these pieces. So then you have to record all of this, right? So there's a 1 stream coming in from this side, there's a 1 coming in from this corner. So each lattice point that you go to, you're going to have to look at all of its boundaries and see if it's got an incipient stream coming in, and then look at its orders. So you'll have to do this iteratively, right? You'd find all the 1s first, you'd label all of those. Welcome, right? 1s, 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 1s. Yep, and then when 2 1s come together, so this is an unusual, I know what that is. It's turning, sorry. It's a trifurcation, right? So you don't really see this much, but it's going to happen in these sort of this made up thing. So we'd say this is 2 1s hitting each other, so this is going to be a 2. These are 1s hitting a 2, so that will stay as a 2, right? It doesn't change. So we could make this this will be a 2 like this, and so on. Does that make sense? And missed a 1 here. So this will be 1, this is still a 1. 2 1s hit each other, they make a 2, right? So this becomes a 2 here. You can tell me when I'm making mistakes. Hopefully I'm not making mistakes, but that's what happens. Right. Right, we have these new buildings, right? Innovation and discovery. We talked about this, right? There should be, I've made a horrible mistake and it's on fire, or other actual science terms. What was I doing? Or do you want to play table tennis? That would be another one. High quality science. So let's make an orange one. So these are sort of weird things you wouldn't see at large scales, but this will be a 3, right? And so there's a 2 hitting a 3, but that's just going to get absorbed. This is this idea of absorption, and so the whole thing would be a basin of order 3. Is that sort of all right? Yeah. Did I get this wrong?
Just a quick question. So we talk about how are we not looking at, like, so ones connecting at the same point create two?
Two ones hitting each other, yeah.
Yes. So
This, I do think this could all be done better, but this has been around for 60, 70 years, and yeah.
yeah, just like,
Yep.
why would not two ones hitting necessarily at the same spot create another two? Like, it seems like at some point, like if I just have ones and ones and ones and ones,
Yeah.
is it really just going to stay at two? Because that just doesn't seem plausible. Like, I understand that you're absorbed, but
Yeah, no, fair enough.
the river's going to have more water flowing into it.
It turns out that this stream ordering, it sort of works well enough for you to be able to kind of go up through all the statistics and get to power laws and so on. But it does, and the Tokunaga stuff, which we just got to and I didn't quite finish, shows that there's really nice structure in terms of those side ones, right? So that they can be counted in a nice way. However, I think it could be done much better, yeah. Because once you look at the distributions for things like area, basin area, and stream length, or volume in bodies, whatever it is, they're these kind of very broad distributions, which shows you, and we saw some examples for the Mississippi, like an order 8 or an order 9 could be quite small. So that's not really right. It's not really the right thing. So this will work well. I mean, it works well. As far as creating a taxonomy, it doesn't connect to the physics as well. That's the thing. So if you wanted to think about, so this is blood networks, of course. River networks. We're thinking of stuff flowing out. If we're thinking about blood networks, we're thinking about flowing in and flowing out as well, right? So we've got the arterial network, and then there'll be this venal network which is attached to it, which has some different properties because it's returning. Then you think, and we'll get to this later on when we get to optimal networks, you have to think about what's the impedance of this thing. And it's very much a kind of a hydraulic story, which is analogous to electrical circuits as well, right? So that you're trying to push this material up here, blood or fluid of any kind, and there's resistance in the tubes and all sorts of things. So, what does this, if you've got a heart here pumping or something just continuously pushing, what does it see this network as? And how would structuring the network in different ways change that impedance? So it's hard to calculate. So what I'm trying to say is it is a bit difficult to calculate the impedance of this thing using stream ordering. There must be a better way to do it. So you should think of that. It'd be really great, actually, to improve upon this. I mean, this has all sorts of goodness that I'll show you, but I think there's another way we could go potentially. Lara. Does everyone have a node in them? Yeah, so you imagine that there's rainfall, so this is a bit odd, obviously, because it's high variability when it comes to rainfall, but we sort of just imagine this over a long period of time, this sort of steady state rainfall. And the way you do it in a simulation is you just have, so this is a lot like Minecraft with irregular shaped heights and so on, right? And I really thought I'll reference Minecraft a little bit, but you imagine your big block of fluid coming down or a bowl, and it hits it and it falls off and flows down through this thing. But that's happening at every point. So you've got this sort of just steady stream of these little blocks coming down, and then they flow down. And so if you think about this in a steady state thing, if you look at this at every time, and it's kind of, right, it hits here and then falls off, hits here and falls off. So if you looked at this, there'd be this sort of this depth of 1. I mean, it's all normalized however you want, but there's sort of depth of 1 here. But this one would have, and we'll get to this now, I guess, there's going to be 1 falling here, but it's also going to be getting this one every clock cycle. And you could, there's a square root of 2 here you could play with. But, so that's all right, so this is a good place to talk about this. So there's 1 area there, 1 area there, 1 area there, but this one has, so the 1 is, so you combine things, right? You'll see 1 plus 1 plus 1 plus 1 here. So this is actually a 4. So the drainage, and so this makes sense when you look at it, right? This is the basin area for this thing is 4. So your little algorithm, the way to do this is you go to every point and you drop a little block down and you let it fall down the path of steepest descent. And every time you go to a point, you put a bean there. I'm confusing beans and blocks and things. But you imagine a little raindrop, it falls here, and then next time cycle there'll be another raindrop. So let's imagine there's only rain falls in this square. All right, so we just let it do this continuously, and eventually there'll be just this flow of the stream that's coming down, and it's all sourced from that point. But it means it'll start piling up.
Maybe just to clarify the underlying data here, you're looking at elevation within each grid cell?
Yeah. So I kind of got this out of order, and so it's going to be like this, right? So let me come back to this one, but I was just trying to sketch this out last night. So this is the sort of thing you get from satellite data. It's been cleaned up and so on, and put on a big square grid. These are USGS, we'll call them digital elevation models. There are irregular heights, but the squares are sort of made to be uniform. There's curvature of the Earth to worry about a little bit, but basically, these are big matrices. You have a big matrix for the US or whatever you want, and then you imagine water falling down this thing, and that's how you extract the paths. All right, so maybe I should stay here. Did you want to say something more?
Well, just
You do.
there's sort of two related things happening. One is the elevation of the Earth's slope, which is the difference between the value of elevation and the
Yes, right. So let's see if we can kind of show it. So here's say the data we've got out, and imagine you can't see it on this, but I hashed this. There's a wall here and a wall here, right? So nothing's going to fall off the back. This is some sort of weird Qbert game. Yes, Qbert. Poor sad Qbert, who probably none of you, unless you've seen Wreck-It Ralph. Qbert is homeless in Wreck-It Ralph. It's very sad. They pulled the machine out. Okay. All right. Okay, so we imagine here's our little raindrop. It's going to bounce off, and we're imagining you can only go in one of the 4 directions here. So it's going to find the steepest descent. Yeah. So this is the lowest one that's adjacent to it. This one is lower, so it's going to go boink, 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 and then fall off in some direction here. And so you do that for every one of these points, and you start to get a network structure. It's going to be more complicated when you allow the 8 directions, and then we've got a square root of 2, so the slope, it's not just the lowest point, because there's you have to divide by a square root of 2 to figure that out. So let's imagine, in fact, that this is lower, this is steeper, I should say, from here to here, but not this one, right? So this is the steepest one, and then it bounces off in this direction. And if you do that, I guess that was sort of the idea. You start to build this sort of network that when you look down on you get one of the examples, the sort of the example I just showed you, right? So that this one flows down this way, these ones would flow off in this direction, and they start to form a network structure. You can't get looping in this, right? I mean, if there's sort of equal heights, you could just do a random choice and fix it. There is one difficult problem, which when you've got a large continent scale thing that you wouldn't get for blood networks, is that there are lakes. And more than just lakes, because you've got some resolution, maybe it's whatever it is, 1,000 meters or something like that. There'll just be patches in here that are just lower than everything else, right? So they're little sinks. So your little algorithm's going along and dropping things down, and it's all falling down, and then it just gets stuck. So to deal with that, you have to go in and find all of those places you get stuck where you didn't reach the border of the data set, and fill it up and just make it a little bit higher than the next lowest one. So I have an old C code that I did for this. And so when you've got a big enough lake, I mean, the Great Lakes, right? I mean, these are big, sizable things. Is actually, so you'll have a whole patch that everything's the same height, because the resolution of the satellite data is such that it's the same height. So the way to do that is you go to the edge of the thing. So imagine this is our lake. You go to the edge of it, and you find the steepest points off it, and then just add this very thin, like, gradient going out from it, sort of fanning out from it. So anything that comes down off a mountain here will eventually roll off the edge. So it's just a sort of a way of filling it in to allow this simple algorithm of things falling down the steepest descent to work. So you have to treat it first to make sure that there is an exit point for everything that flows down. I think that code was called kevinlakewaster.c for some reason. Anyway, so that that's tricky. That's a bit of a trickiness, but I'm not going to make you do that, if that's okay. Is that all right? So this is a good thing to work on. So we have these characters here, right? So there's one here, one here. Let's just get to a little bit. This one is going to be a 3, right? So it's because I rotated it. And how do I do this again? I want to, where's the thing? I've lost my, oh, here it is. All right, hook. Yep. Good, okay. Woohoo. All right. So we'll do just a few more. So there's a 1s here, 1 here. And there's this little +1 for this one, but it's getting 4 from here and 1 here. So this turns out to be 7, which, you can see, right? It is that area that's being drained. So this will be 11 once we get to this. Right, so you can make a little algorithm do that. This sort of thing, so you want to find the longest stream. So this is different. Now you have to go back up through the network, and we'll have square roots and so on, but the longest stream in this one, maybe, for example, you might go, it looks like it would be, either this way or this way. Well, no, it's actually going to be that way, because of the square root of 2. Oh yeah, there's a whole extra one. Good, thank you. Yeah. Did not see it. Oh gosh, I've got to do all that. I was trying to be lazy. So 1, 1, 1. So we're going to have a 4 here. It's easy sort of to not count the, no, that's 1, 1, and 1. So 3. 1 plus 1 plus 1 is 3. Okay. What do we got? It looks like 15. 3, 3. So 6, 7, 14, 15. Is that right? And so that would be this whole basin. Yeah, 5 by 3, right? If we take this block and put that here, we've got a 3 by 5, so 15. So it will, and so it means that this one will be, you'll get a 25 here, whatever happens, because there are 25 things. Okay, so that's sort of the strategy for figuring some of these pieces out. You can see it requires you to kind of record a lot of things and maybe sometimes go backwards up through the network. Sometimes it's a simple descent thing, but yeah, a little bit tricky. And again, for blood networks, this is going to be a harder thing once we've got it stored in some way. It's going to be in some sort of three-dimensional messy thing. Ideally, you get it down to here are junction points, and they connect off and connect off. Yeah. It's all right. So that was my little extra bit there. Oh, I just destroyed it. Okay. Oof. Okay. Okay. So it's all right? Lara. So you'd start with this one having is that what you're saying? Like this has a length of 1 in here. You just sort of give it a little piece. Yeah. So what you need to be able to do is as you go back up through here, you see how you calculate the mainstream lengths for all these little sub-basins, and as you go up here, you go into the longest direction. So you can make it work in this direction too, I suppose. That's true.
So is it like for each little dot, or is it some mainstream lengths?
Yeah. So that's an important thing about these things, and with us as well, right? Is that there are basins within basins. So every dot has its own basin attached to it. So there's a tiny basin for this one. This one drains this whole area. So each point has its own little basin, which has an area and a longest length and a typical shape. Is that okay? Yeah. So this point here, this is its basin, the whole thing, and that's its longest stream. This one, it's just got this little basin, and yeah. So it's an interesting thing to think about. You have to, and I'll show you some other kind of interesting pieces about this that I don't think have been figured out, but you have this kind of weird packing problem. It's easy, you have all these basins, but of course they're all overlapping, so you have to be a little careful about that. And this shows you one of the reasons, right. So this is an extra piece. Okay, Tokunaga, as I said, this is work that came out of Japan and wasn't really known outside of Japan for about 30 years. But it built on Horton's work, which was from the 40s. And so these are these order 1 basins on the side that are going into this order 3 stream here. And there are order 1s here going into these order 2s, right? When you think about this, it's a bit of an odd business, right? The order 1s comprise some fraction, if you take all of their areas, it comprises some fraction of the overall landscape. The order 2s as well, right? They comprise some fraction in the order 3s. So, what's that fraction, right? So it turns out that they don't really take up all of space, which is a bit odd. All right, we'll get to that later on. Okay, so here's the idea. We're absorbing streams of order nu into streams of order mu, right? So this could be a 7-order stream, gets a stream of order 5 coming in, and we want to be able to count those things. And so the observation was around these couple of steps. So the first one is based on just a heuristic of, you can assert this essentially, and then sort of test it out, but it's a reasonable thing to think beforehand, is that the difference between the absorbing stream and the stream that's entering it is all that should matter, right? So that once we're away from the order 1 ones and the overall order of the whole thing, there should be enough self-similarity in these systems, which we evidently see that this will be true. So that takes out, it reduces the parameter set, right? So now we've really just got the difference, so that's the difference in here. And if that's true, then there's an extra piece, which is that, like Horton's laws, and there'll be a scaling, right? So that if we set the difference to be 1, right? So if this difference is 1, so we're talking about how many order 6s go into an order 7, or how many order 9s go into an order 10, then this is to the power of 0, right? And so the idea here is there's a typical number of streams of order 2 in this case that go into an order 3, or order 1s that go into an order 2, and so on. And from there, there's this ratio that you scale up with, right? So roughly in this case, well, I'll have an example. But roughly in this little example over here, the ratio is 2. This Tokunaga ratio is 2. You start off with about 2 as well. But usually usually this is around 2. Usually this is around 1 or something. Is that sort of okay? So this is this is an observation. So there's a nice thing to connect, right? So here's our example at a bigger scale. All right. So the first one, and so this is made up, of course, is roughly 2, right? So of course it's made up. So there are 2 side streams of order 2 here. In this one it has 1, 2, 3. It's statistical, of course. 1, 2, and then up here there's only 1 in this case, and then 1 and 2 here, if you can see all these things. But the number of order 1s going into the 3 here is 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, it's probabilistic. Of course, the numbers have to be integers. But this is roughly the idea that if you look at a certain order and then you look at how many side streams of the order below, you'll see roughly 2 on average. And then as you move up through the differences, you'll get a factor of 4. So there should be roughly 8, and in this case there were 9 order 1s going into order 3s. There'll be 16 order 4s going into order 7s, and so on. And so this turns out to be, this is a reasonable thing to suggest. I mean, once you realize it's not a pure hierarchical structure. Again, that's true of us. So this is a really, I think, an important, while the stream ordering thing is not perfect for, say, physics, this does give us something important to understand, that it's not a pure hierarchy, right? That there are these small pieces going into large ones. Which I don't know if you'd suspect that straight away. So this is to show you some data. It's a little bit messy, of course, as you might expect, and it's going to fall apart at the ends. But this is this Tokunaga ratio as a function of mu, which is the absorbing stream. And then each one of these lines is for a particular stream order that's being absorbed, right? So these are order 1s going into order 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s, right? So that has to go up. Fair enough? And this is just orders across here. This is a log scale, so it's increasing exponentially, which is what a strict ratio should do. It's rolling over a little bit. It's going to fall apart at that largest scale, which is fair enough. It should be a little bit messy, perhaps, at this for order 1s, because that's, again, the other end of the resolution. But it's not too bad, right? So if we look at, say, order 3s, that's here, going into order 4s, and then 5, 6, 7, 8s. It's not bad scaling here, and then it's going to fall apart. So this is, and then you see some real aberrations at points. So that seems to hold up pretty well. Scaling is very messy, and if you want to look at these things, it's hard. Yeah. So along here, this is just, these ones are the ones where you're looking at the order below, right? These are 1s into 2s, 2s into 3s, 3s into 4s. And they sort of have a bit of a drop. That's fair enough. So that seems like that's one end of this scaling that you expect to maybe be problematic. Right, so there's a bit of it's not great here, and then it's going to fall apart at this other end. And we expect that. Anyway, this shows you it's not bad, and that this is really part of the fabric of these kinds of networks. Again, understanding these things is hard. I have a whole bunch of, so I just fell short of getting there, but of course I've added more stuff, so it's fair enough. Before we go into the second section. So a lot of self-similarity, as we've seen, right? And I've focused on river networks, but we'll get more to the blood network data soon. Where there really are these beautiful theories, too, for why the networks are the way they are. We'll see that they are problematic in interesting ways. Okay, so lots of interrelated scaling laws. I gave you that big list, sort of as the Horton Strahler. So the stream ordering is a way to get at the architecture. And if you think about this, maybe you can come up with a better way to do it. But it's been around for a long time, and it's been transported into lots of different areas where branching networks are around. Even people thinking about like seaweed and stuff like that, right? So anything where there's some structure. I really need to do phyllotaxis. Okay, so self-similarity, and this is really the first kind of quantification of fractal structures, as I understand it. Again in the 1940s, didn't have the word then. It was Mandelbrot, but 20 years later. Right, not a pure hierarchy. Tokunaga really helps. So Horton's laws alone do not give you, so you can't really get Tokunaga's laws. Well, you kind of can, but they don't imply it in a very clear way. And so we'll sort of go through that in the next set of slides. I know it's exciting. So there's a mixed hierarchical structure. These things can be connected. And then surprisingly, there's this sort of thing, right? So this is a bit odd, perhaps, right? It's not obvious straight away. But this is the Horton ratio for stream number. And sitting out here are the pieces floating around from the Takanaga's law. Right? So that's the ratio, and that's the number for the number of side streams of one order less. So there's some quadratic involved, obviously, right? But it's a little bit odd. And there are some perfect kind of contrived examples that fit together very well. So if you have 2 and 1, for example, I think, yes, then, yeah, which is not a bad little sort of network to play around with, right? So this would be 5 squared minus 16. So 25 minus 16, we're quite excited about that little Pythagorean triangle, right? So there'll be a plus 3 here. 5 plus 3 divided by 2 gives you a 4. So that's actually sort of not, that's just a lot. it means that you can make some examples that have integers everywhere, which is sort of nice. But there are random network ones where there's no analytic solution for these things, even though they're nice random walk type things. We don't know what these are. We know what the power laws are. Okay, all right, so that'll be a good thing to figure out. Yeah, okay. This is a ridiculous thing, but I did mention Minecraft, and that's a pretty interesting landscape, and it's hard to build a landscape that keeps going, right? So this is just to finish this is for charity, but basically the plan has been to go in one direction in Minecraft and just keep going. And, it's made in such a way that, and then just video, just video running around with this thing. So this is just ridiculous.
Hello, ladies and gentlemen. My name is Kurt. Welcome back.
So that's number 670. So it's 40 minutes to 50 minutes. This guy's just been doing this for years and years and years, and it's turned into something where he's getting funding. But he's still, I guess the idea is to get to the point of where Minecraft just falls apart, right? Because it's still creating landscape. You start to get some aberrations, but yeah, it's it's still, and it's consistent, right? So if you go back, it'll be like what it was, but it gets to be you start to run into some issues with numbers. Yes, it's impressive though. Yeah. Yeah, there are some issues that I think there's been some bad moments where he's lost things, but he's survived. So he has his dog, he has his little pal called Woofy, so it's all very nice. It's kind of incredible, Minecraft, I guess. But I know. My daughter's had a total field day with it for a couple of years, and then it's gone. And it's gone. Like, this is uncool. This is super uncool now. Just gone. They built pirate ships and all sorts. It was pretty great. They actually played together. It was amazing. Well, one of them told the other one what to do. Let's see. Let's be honest.